Today we are going to discuss the wave equations for different medias. So, to derive different wave equations for electromagnetic wave, we have to consider some initial parameters. Now, this wave will propagate through different media, and for each media there are some quantities are 0, for some media some quantities are greater than 0. So, which quantities are 0 and which are greater than 0, that we have to consider, and accordingly the equations will change. So, first we will consider wave propagation in lossless medium. So, for this lossless medium, lossless means there will not be any loss of the amplitude of the electric field or magnetic field, no loss of the frequency, no distortion will occur. So, this kind of medium is called as lossless medium. A medium is called as lossless when sigma is equal to 0. Okay, when sigma is equal to 0. Sigma is equal to 0, and other parameters like epsilon is equal to considered as epsilon naught into epsilon r, and mu is considered as mu naught into mu r. Okay, and we have seen this ratio sigma divided by omega into epsilon. In case of when we take the ratio of two conductivities, displacement current density and conduction current density, then it is giving us this ratio sigma upon omega epsilon. Sigma is called as conductivity of the medium. So, as this conductivity is 0, this ratio will become very less than 1. So, for lossless media, three considerations we have to consider: sigma should be 0, epsilon is equal to epsilon naught epsilon r, and mu is equal to mu naught into mu r. Okay. Then for the second media, that is for, let us consider the wave propagation in air or free space. Air or free space. For air or free space, sigma is also again considered as 0, but epsilon is considered as epsilon naught and mu is considered as mu naught. Therefore, these parameters can be used in the respective wave equation. Now, third category, wave propagation. Wave can propagate through a lossy medium. Lossy medium means where the amplitude distortion will occur, or there is a loss of amplitude of electric field or magnetic field of the wave when it travels through that particular medium. So, for lossy medium, why this happens? Because there is some kind of conductivity present. So, sigma is not equal to 0 for those medium. Sigma is not equal to 0, and epsilon will be present. So, epsilon is equal to, again we will consider epsilon naught epsilon r, and mu will consider as mu naught into mu r, and that particular ratio sigma upon omega epsilon will become greater than 1 for lossy media, because there is some value for sigma, that is conductivity, hence it will become greater than 1. Okay, so, this is the third media, and the fourth media is wave propagation will consider for good conductor. Okay, so, for good conductor, again we will consider sigma is nearly equal to infinity, sigma is very high. Okay, and epsilon is, again we will consider epsilon will consider as epsilon is equal to epsilon naught into epsilon r. Okay, and mu is considered as mu naught into mu r, but sigma is nearly equal to infinity. So, that ratio sigma divided by omega epsilon will become very greater than 1. For good conductor, sigma is very high in terms of some mega Siemens per meter and so on. So this ratio will become high. So according to that, by using this ratio also we can judge whether the material is good conductor or good dielectric and so on. Okay. So and fifth one, for good dielectric, wave can propagate through good dielectric, but good dielectric is nothing but a lossless media. So we will consider all the equations of lossless media. Air is also called as a dielectric material. So we can consider, if it is perfectly air, then it is again a dielectric material. So we will consider epsilon is equal to epsilon naught and mu is equal to mu naught. If it is not a air and if it is an other dielectric material, then we should consider sigma, or sorry, mu is equal to mu naught and epsilon is equal to epsilon naught. Right. So with these notations, let us proceed further. Now we have to consider some another notations that we already know, and we will start with using Maxwell's equation. Okay. So wave equations derivations will start with using Maxwell's equation. So here we are going to consider the Maxwell's equation for time varying fields. Okay, and we will modify those Maxwell's equations according to the media. Whatever we want, we will change, but we will start with what? Time varying fields. Right. So what are the equations of time varying fields? First equation is del cross E bar is equal to minus B bar dot. Del cross H bar is equal to D bar dot, and del dot D bar is equal to 0. Okay. But for time varying fields it was rho v. Okay. But for lossless media as rho v is also 0, therefore this del dot D will become 0. Okay. Here also there was J present, but for lossless media as sigma is equal to 0, this J will also become 0. So it will be only D bar dot. Okay. So we are going to derive equations for lossless media. And one more we have left with, that is Gauss law for magnetic field, del dot B bar is equal to 0. So we will consider all these 4 equations. We will consider all these 4 equations. Del cross E bar is equal to B bar minus B bar dot, and del cross H bar is equal to D bar dot, and del dot D bar is equal to 0, and del dot B bar is equal to 0. So with this equation we are going to derive the equation, general equation for a wave. Okay. Again we will consider some formulas we know already. So what are those formulas? We have D bar is equal to epsilon into E bar, that we already know. If I take the derivative of D bar, then it is become derivative with respect to time, means D bar dot, right. So now this will change this right hand side to epsilon E bar dot, right. Then for free space, so again one more the identity is there, B bar is equal to mu into H bar. So if I take the time derivative of B bar, then it is nothing but B bar dot, time derivative is nothing but adding a dot sign. So it is mu into H dot. Okay. Similarly, if I take, suppose B dot is already there, and if I take the time derivative of this equation, then it will become B double dot is equal to mu into H double dot. This is also valid. Okay. Similarly, J we know as sigma into E bar. So if I take the dot of J, then it will become sigma into E dot also, right. Again for free space, mu we will consider mu naught and epsilon we will consider as epsilon naught, right. So for if it is air, but if it is other than air, then we will consider mu is equal to mu naught into mu r, and epsilon is equal to epsilon naught into epsilon r, other lossless media. but we will consider with this, we will consider mu is equal to mu naught mu r and epsilon is equal to epsilon naught epsilon r. We will use mu and epsilon. So, with this notations, let us start deriving the equations. Again there is one more thing, del cross H we know as d bar dot, right. Now, if I take the derivative of both sides, dou by dou t of del cross H bar, then it is equal to dou by dou t of d bar dot, then del cross H bar H dot will become, because it is time derivative, so it is equal to d double dot. This is one more important notations we are going to use. And similarly, if I use del cross E, okay, it is equal to minus b bar dot, and if I take the time derivative of both sides, then it is del cross E bar dot is equal to minus b bar double dot. This is one more equation we are going to use further. Okay, so with this all the assumptions, let us start deriving the wave equations. Now, there are two types of fields, two fields in a wave. One is electric field and the other one is magnetic field. So, we will consider which is the Maxwell's equation where electric field is used. Let us start deriving the equations. So, as there are two fields, we will start with electric field. Okay. So, for electric field, the Maxwell's equation is del cross E bar is equal to minus b bar dot. Now, taking curl on both sides. This is equation number 1. So, if I take the curl, it is del cross E bar, which is equal to del cross b bar dot, and that is equal to del cross minus mu into h dot, because b bar is equal to what? Mu into h. That is equal to, let us take mu constant minus mu outside, and it is nothing but into bracket del cross h bar dot, right. But what is del cross h bar? We have just derived del cross h bar is equal to d bar dot. Okay, so del cross h dot is there, so it is equal to d double dot. So it is minus mu into d bar double dot, which is also equal to, now d bar is equal to mu epsilon into E bar, right. So it is equal to minus mu epsilon E double dot. So this is our equation number 2. So I will write it again. Okay, del cross E bar is equal to minus mu epsilon E double dot. Okay, equation number 2. But del cross E bar is equal to, there is a vector identity, that is del cross E bar is equal to del in bracket del dot E bar gradient of divergence of E bar minus del square E bar. This del square operator is called as a Laplacian operator, and it is double space derivative, means dou 2 x by dou 2 divided by dou x square, dou 2 divided by dou y square, and so on, of whatever the vector quantity given. So it is called as a Laplacian operator. And what we know, del dot E bar is equal to 0. Why? Because del dot D bar is equal to 0, and since D bar is equal to epsilon naught E bar, it will be del dot E bar is equal to 0. So finally del cross E bar is equal to, this quantity is 0, so I will put it 0 minus del square E. Okay, so that is equal to del cross E bar is equal to minus del square E bar. So this is equation number 3. So from equation number 2 and from equation number 3, we will equate these two equations, and what we get, minus del square E bar is equal to minus mu epsilon E double dot, or we can write del square E bar is equal to mu, after neglecting the negative sign, it is E double dot. So this is first equation for electric field. Okay. Second part, for magnetic field, we will consider second Maxwell's equation, del cross H bar, where magnetic field comes, H is magnetic field quantity, so it is minus B bar dot. So taking curl, again same thing we will do on both sides. What do we get? Del cross H bar is equal to del cross minus B bar dot. Then it is equal to del cross H bar is equal to del cross B bar dot is there, so minus B bar dot is there, so minus I will take the outside, and del cross, it will become B bar is nothing but mu into H bar dot, right, and then sorry, secondly, we are going to derive the equations for magnetic field. So for magnetic field, we will consider Maxwell's second equation, and that is del cross H bar is equal to D bar dot, right. So this is magnetic field and this is electric field. Always Maxwell's equation relate two fields. Now taking curl on both sides, so it is del cross H bar is equal to del cross D bar dot, right. So it is del cross epsilon into E bar dot, that is equal to epsilon in bracket del cross E bar dot. We will call this as equation 1 for magnetic field, equation 2 for magnetic field. But what is del cross E bar dot? What is del cross E bar dot? We have written something as an identity in the previous equations. So that is del cross E bar dot is equal to minus B bar dot. So epsilon into bracket minus B bar double dot it is. Okay, so this we will call it as equation number 2. Now what is next? Del cross H is equal to minus B bar dot double dot, and there is one more thing, that is epsilon. So it is epsilon into B double dot, that is equal to minus mu into epsilon into H double dot, because B bar is equal to mu into H bar. So this is the third equation. Now as previously said, del cross H can be written as an identity, and it is equal to del dot H bar minus del square H bar, but this is 0, del dot H bar is equal to 0. Why? Because del dot B bar is equal to 0. hence del dot h bar is also 0. So del cross h bar will become minus del square h, since this is 0. Okay, so from equation 3 and 4, what we can write? Minus del square h bar is equal to minus mu epsilon h double dot, or del square h is equal to mu epsilon h double dot. So this is equation of wave for magnetic field. This is equation of wave for magnetic field. Now these equations are called as general form of equations. Del square is called as a space variation, that is dou by dou x square of h plus dou 2 h by dou y square plus dou 2 h by dou z square, like that, and it is Laplacian operator. So it shows a space variation. And what is double dot variation? That is equal to time variation. So that is dou t square of h quantity, hx quantity, or dou 2 hy with respect to time, and dou 2 hz with respect to time. So this means space variation is equated with time variation, right? So this means electromagnetic waves moves in space, either x axis or y axis or z axis, and along with that it is moving with respect to time. The time variation may be sinusoidal time variation also. Okay, so in this way we can say that this equation is a general form of Maxwell's equation for magnetic field, and this equation, the previous equation, is called as general form of Maxwell's equation for electric field. Now we are going to find out what is the solution of these equations later on. Before going to the solution of wave equations, let us examine what do you mean by plane electromagnetic waves. So consider that, for simplicity, that an electromagnetic wave is propagating in z direction, positive z direction, with electric field is pointing towards positive x direction, and magnetic field is pointing towards positive y direction. So after every cycle this is repeated. Now here in the first figure, the electric field is pointing towards x direction and magnetic field is pointing towards y direction. The wave is moving towards z direction. Okay, so if you take the perpendicular slices of this kind of wave, then we will get similar kind of fields, E field and H field. They will remain, their values will remain similar as before. So there is one more concept of uniform plane wave. An electromagnetic wave which originates from one point in free space and spreads out uniformly in all directions, and it forms a spherical wavefront. It's called as uniform plane wave. Means for every slice the E field and H field is remaining constant, and it is perpendicular, exactly perpendicular to each other. Okay, so if this wave is moving in a space towards z direction, it looks like as a circular omnidirectional wavefront, because this E field and H field is rotating at every half cycle. An observer at a large distance from the source is able to observe only a small part of wave, and wave appears to him as a plane wave. So it is called as a plane wave. Plane wave means like this. For such a wave, electric field and magnetic field are perpendicular to each other, and they are perpendicular to direction of propagation also. So everything first E and H are perpendicular, and both of these are perpendicular to the direction of propagation. So in every plane, E and H field are showing perpendicular to each other. A uniform plane wave is one in which E and H lie in a plane and have same value everywhere in the plane at any fixed point. Okay, so their value will be stable if you take fixed points. So for this kind of waves, we are going to derive the solution. So for an uniform plane wave traveling in z direction, the space variation of E and H are 0. So there is no variation of E in z direction, no variation of H in z direction over z equal to constant plane, right? So it implies that the field have neither x nor y dependence. They will not depend on x variation and they will not depend upon the y variation. So this means dou by dou x variation and dou by dou y variation of that particular wave is equal to 0. It has ex component, it has ey component, it has hx component, it has hy component, but the variation with respect to x, variation with respect to y is not there. Right, it is variation with respect to z is there only because it is moving towards z axis, right? So ex exists, ey exists, hx exists, hy exists, but dou by dou x, dou by dou y is equal to 0. Such a plane wave is called as a transverse wave and it is called as a transverse in nature. That is, E bar and H bar both are perpendicular to the direction of propagation. So they are called as TEM wave, that is transverse electromagnetic waves. Now consider such a uniform plane wave propagating in z direction. So it will have, as I said, hx, ex, ey components but no ez component. So ez is equal to 0 as stated at the second line. There is no variation of these field components along x axis, x direction and y direction. See in the figure. This wave has ex component and hy component. At the second half cycle, it has minus ey component and minus hx component and so on. But there is no ez component or no hz component here. But they are moving towards z axis. So there is no variation with respect to x axis, no variation with respect to y axis, but there is a variation along z axis, right? So there is no variation of the field components along xy direction. So we consider that dou E by dou x or dou E by dou y is equal to 0. Wave equation for free space therefore is given by, we know already this equation, we just derived this equation, dou 2E is equal to mu epsilon, or if it is a free space then it is mu naught epsilon naught dou square E by dou t square. This is the general form of equations just we have seen. But what is dou 2E? This is Laplacian operator and Laplacian operator is given by dou by dou x square, dou 2 by dou y square, dou 2 by dou z square. Now E has all the components. If you consider E in Cartesian system, then it is expressed as E bar is equal to what? What is E bar in Cartesian system? It is Ex Ax plus Ey Ay plus Ez Az. Now we are applying this Laplacian operator to E vector. So what we got? Dou 2 by dou x square plus dou 2 by dou y square plus dou 2 by dou z square. All things are applied to Ex Ax component. Then plus again the same Laplacian operator is applied to Ey Ay component and then Ez Az component. Same thing is applied for all Ex, Ey and Ez component. This is our right hand side. And what is left hand side? Mu naught epsilon naught is as it is. Now there is a variation of E again with respect to time t. So dou 2 by dou t square Ex Ax plus Ey Ay plus Ez Az. Okay. Now we'll equate Ex Ax component together. So after equating, what we get? So Ez is 0. So is there in Ez? Yes, Ez Az is there in the third part. So this is 0. So we'll neglect this term. Okay. So we are left with these first two terms. Now there is no variation with respect to x, no variation with respect to y, as I've stated here. So only there is a variation with respect to z of which component? Ex component. Variation of with respect to z of ey component. So we'll consider only those variations. Okay, so Ez is equal to 0 and dou Ex by dou x and dou Ey by dou x are 0. So dou 2 Ex by dou x square and dou 2 Ey by dou y square are also 0. So from equation 1 what we get? So there is variation with respect to z axis only. So here we have considered dou z square of which component? Ex component. So dou 2 Ex by dou z square into Ax plus dou 2 Ey by dou z square into Ay is equal to epsilon naught mu naught into epsilon naught into dou square by dou t square Ex Ax plus Ey Ay. Now we can equate left hand side and right hand side. So this part is equal to this much part. So after equating, what we get? Dou 2 Ex by dou z square is equal to mu naught epsilon naught dou 2 Ex by dou t square. Variation of Ex with respect to z axis is equal to mu naught epsilon naught variation of Ex with respect to time. And similarly, what second equation we got is dou 2 Ey by dou z square is equal to mu naught epsilon naught into dou 2 Ey by dou t square. Similarly, for h component we obtain the similar equation. So look at this equation carefully. Let me zoom this equation. Just check these equations. So here it is space variation, this side it shows time variation. Here it is space variation, at the left hand side, right hand side it is time variation for all E component as well as H component. E has X component, H has X component, E has Y component and H has also Y component. Okay, so next, so finally we can write that for a wave which is traveling in Z direction, we can write all those equations again. Same equations are written one by one. Then, so to find the solution of this equation, we have to find out the solution. So let us consider that E, if we consider only Ey component, then the solution of this equation is given by Ey is equal to f of some function of x minus v naught t. Okay, solution of this equation, the previous equations, that is the equation just stated here. Okay, let us consider this equation. For this equation, what is the solution? The solution is Ey is equal to some function f of x minus v naught t, where v naught is the velocity with which wave is traveling. V naught is the velocity with which wave is traveling, and that velocity is given by v naught is equal to 1 upon square root of mu naught into epsilon naught. If the medium is other than air, then it is equal to v is equal to 1 upon square root of mu into epsilon. And if it is air, then we know the value of mu naught, it is equal to 4 pi into 10 raised to minus 7. Epsilon naught has a value of 8.854 into 10 raised to minus 12. So if we put these values, then we'll get 3 into 10 raised to 8 per meter per second. What does it mean? It means that the electromagnetic wave travels with the speed of light. Okay, so this is the velocity of light, 3 into 10 raised to minus 3 into 10 raised to 8 meter per second. So electromagnetic wave is travels with the velocity of light, and it is also known by the another letter small c. Okay, and it is 3 into 10 raised to 8 meter per second. So if we plot the wave, this wave, how it travels, then it travels like this. If suppose that f is a sinusoidal function, like Ey is equal to sine of x minus v naught t, for different values of t is equal to 0, t is equal to 1, t is equal to t2 for at different instances t1, t2, t3. If you plot this function ey, then we can see that it is traveling like this. The wave is traveling in z direction. It is changing in its amplitude at every instant of time, and this E field is pointing towards y. Suppose that E field is only pointed and it is pointing towards y direction. If we write the solution of hx component, then it may be some hx is equal to some function x into what, x minus v naught t, or y minus v naught t. Then we can write the similar equations for h also. So finally, this is the expression, or this is the way the wave can look like, or we can find the solution. So at the last, the conclusions made by seeing the electromagnetic equations are: first, a wave has electric field and magnetic field. Second, when wave travels in particular direction, the field associated with it also travels in the same direction. Okay, so E field and H field are traveling in, suppose, Z direction. By assuming that E bar and H bar is a function of x only, we have made the wave travel in x direction. If there is E is varying with respect to x and if H is also varying with respect to x, then we can say that the wave is traveling in x direction. If we want that the wave travel in y or z direction, then the assumption should be that the E and H should vary with respect to y and z. Fourth one, for a wave traveling in y direction, we can prove that Ey is equal to Hy is equal to 0. And Ex, Ez, Hx, Hz constitute a wave in y direction. Suppose that the wave is traveling in y direction, then we can say that there is Ey component is 0, Hy component is also 0. But that wave have Ex component and Ez component, or Hx component or Hz component. So in this way, we can modify the components depending upon the direction of the wave travel. Similarly, we have seen in the equations that wave was traveling in the z direction. So for if it is traveling in the z direction, then Ez component and Hz component is equal to 0, and Ex, Ey, Hx, Hy constitute a wave that is traveling in z direction. All the field components travel with a velocity, and that velocity is given by 1 upon square root of mu into epsilon. So by this notations findings, we can write equations for wave traveling in any of the three directions.